Hello and welcome to 10.2 Infinite Series. In this section we take a look at infinite series and what we can do with them. So we start off with a definition of infinite series. Basic idea of infinite series is that it's a sum of an infinite sequence of numbers. Okay, so if you think about here in this case, this is in generic terms, A1, A2, A3, etc. They define it as an infinite series. AN is the nth term of the series. And we know about the sequence SN. SN will be defined as the sum of n terms in the infinite series. Okay, sometimes they call it a sequence of partial sums. And then we say Sn is the nth partial sum. Okay. Let's see. If we say that we have a sequence of partial sums converges to a limit, we say the series converges and that its sum is L. Okay. If the sequence does not converge, then we say that the series diverges. Okay, so here's an example of how the partial sums work. For example, if we had an infinite series where the first term was 1 and then the second term was 1/2, third term was 1/4, fourth term was 1/8, so on and so forth. Right, to get a partial sum, here we take the 1, partial sum. And then for the second one, 1 plus 1/2, which is 3/2. And here on the right column, you see an expression, a suggestive expression for the partial sum. So as we go forward, we can come up with a formula to come up with the partial sum of n terms. And if we look at a graphic of our partial sum, 1.5 and the 1/4 and 1/8, if we keep adding these terms together, we see that we're approaching the sum of 2. Okay, let's take a look at a geometric series. Geometric series are of this form. We have A and AR squared. Now, how do we come up with that? Well, the first example we looked at, the 1, 1/2, 1/4, this was a geometric series. 1/8. And so we could write the geometric series as if we write the summation notation, n equals 1 to infinity of 1/2 to the n minus 1. So that if we plug 1 in for our first term, we would have 1/2 to the 0, which is 1. For our second term, if we plug 2 in, 2 minus 1 is 1, 1/2 to the 1 is 1/2. Plug 3 in, we get 1/2 squared, which will be 1/4. Again, 4, that would be 1/2 cubed, so 1/8. And so you see how we start to generate the terms of the series. Now, one of the things that we should point out, A is always known as the first term of the series. R is the ratio of the series. Okay, a lot of times when you're looking at the summation notation, R or some version of R can be picked out by the equation by looking at what's being raised to the exponent. Okay, so in this case, in this one, 1/2 would be our R. And our A would be the first term, so it would be 1. Okay, now what we could do, which is nice, we could figure out what this geometric series would sum to. If we were to add up all the terms in the series, we would figure out what that sum would be leading towards. Okay, and that works if your ratio, sometimes we call it the common ratio, if the absolute value of the ratio is less than 1. Okay, if the absolute value of the ratio is less than 1, then the series would converge to this formula. Okay, and that's only if absolute value of R is less than 1. If absolute value of R is greater than 1, then the series will diverge. That means all the terms would be bigger than the preceding terms. Okay. So going back to our previous example, our R was less than 1, right? We had an R of 1/2. So we could use this formula. So R is 1/2, and the formula, this would be the sum. It would be A over 1 minus R. So this would be 1 over 1 minus 1/2. That gives us 1 over 1/2, which will give us 2. Okay, so this series would sum to 2. Okay, let's take a look at this example here. Geometric series with A equals 1/9 and R equals 1/3. So the series would look like this. First term is 1/9. Then to get each term after that, we multiply by 1/3. So next term would be 1/27. Next term after that would be 1 over 81, etc., etc. To write the formula, we would say the formula would be n equals 1 to infinity of 1/9 and then 1/3 to the n minus 1. To get the sum, and we can get the sum here because R is 1/3, the sum would be A over 1 minus R. Okay, so 1/9 over 1 minus 1/3, that would be 2/3. So 1/9 divided by 2/3, that would be 1/9 times 3/2, we can cross cancel by 3. 9 divided by 3 is 3. So we end up with 1/6. Okay, so this series would converge to 1/6. Okay, let's take a look at another example. This series. So first, let's see what this series would look like. Notice this one starts at 0. So if we plug 0 in, so that means we have -1 to 0 is 1, 4 to 0 is 1. So first term would be 5. Okay, so let's keep that somewhere. A is 5. And then to get the next term, let's plug 1 in. 1, 4 to the 1. So -1 to the first is -1, times 5 is -5, and then 4 to the 1 is 4, so we have -5/4. Okay, so we could say 5 minus 5/4. To get the next term, let's plug in 2. So -1 squared is 1, 4 squared is 16, 5 times 1 is 5, so it's 5/16. So it's a positive, so we put plus 5/16. Okay, to get the next term after that, -1 cubed. So that would be -1 times 5 over 64. So -5 over 64. So minus 5 over 64. Okay, so we see what this looks like then. Okay. Now, so we know that A, the first term is 5. Common ratio, okay, this is important. The common ratio, notice we have the -1 to the n and the 4 to the n. Okay, so that is going to be the common ratio. You could just rewrite it as -1/4 to the n. Okay, so another way to write the series, just that portion, you could put the 5 in front, and then it'll be -1/4 to the n. Okay, so common ratio r is -1/4. Okay, so let's take a look at what the sum would be. Okay, so A is 5. And R is -1/4. Okay, so we have A over 1 minus R. Okay, which becomes 5 over 1 plus 1/4. So we have 5 over 5/4, which means this will be 5 times 4/5. So that means our sum, we can cross cancel the 5's, our sum will be 4. Okay, and that's what the series would converge to, 4. All right. Okay, let's take a look at example 3. You drop a ball from A meters above a flat surface. Each time the ball hits the surface, after falling a distance h, it rebounds a distance rh, where r is positive but less than 1. Find the total distance the ball travels up and down. Okay, we see this in the figure. Ball is being dropped, travels A units. On the rebound, it travels AR units up, and it would travel AR units down. So far we have A plus AR plus AR. And then when it comes back up, it would travel AR squared and down AR squared. And it would continue like this. So we have A plus, this would be 2AR plus 2AR squared. And it would continue like that, plus 2AR cubed so we could come up with a partial sum formula for this. Right now we have A, that's the only lone term here that doesn't fit this pattern. For this pattern we could come up with a partial sum. So we would say we keep the A, and then for the partial sum here with the two A's, we would say the first term in that series would be 2AR, and then the denominator would be just like the other case for the partial sum, 1 minus R. Okay, so we could use that to give us the sum. Okay, so for example, let's say A, we dropped the ball from 6 meters. Right, so let's say A is 6. And then let's say R was 2/3. So every time it bounced back up 2/3 of the previous height. Okay, so then we could set this formula. We know that A is 6 plus 2 times 6 times 2/3 over 1 minus 2/3. So let's see what that gives us. So we have 2 times 6 times 2, that's 4 times 6, 24 thirds over 1 minus 2/3 is 1/3. 24 thirds divided by 1/3 would just be 24. So we have 6 plus 24. So that ball would travel a total of 30 meters up and down. Okay. Let's take a look at another example. Express the repeating decimal 5.232323 ... as the ratio of two integers. Okay, so we could write this as 5 plus, now for the first 23, this would be 23 over 100. Right, 23 hundredths. Now, every 23 after that, you could write it as 23. The next 23 would be 23 over 100 squared. The next 23 after that would be 23 over 100 cubed, etc., etc. Okay, and this would continue. So, what we could do then, the piece that has all the 23 and the hundreds, we could factor out a 23 over 100. If we do that, we're left with 1 plus 1 over 100 plus 1 over 100 squared, etc., etc. Okay, we could even do like 1 over 100 squared. So this piece can be considered a series, right? This could be considered a series where A is 1 and R, notice how you're multiplying by 1 over 100. Right, so R will be 1 over 100. And now we can figure out a sum for that series. Right, we would say A over 1 minus 1 over 100. So we have 1 over, and what would that be? 99 right? 100 over 100 minus 1 over 100 would be 99 over 100. Now 1 over 99 over 100, that would be 100 over 99. Okay, so let's get back to this piece. So we have the 5 plus 23 over 100. And then for this parentheses, we just figured out that that was 100 over 99. That's what it converts to. So we could cancel out the hundreds. So we have 5 plus 23 over 99. Okay, and now we can multiply and convert, right, 5 plus 23 over 99 as a ratio of 2 integers, right, because I believe that's what they wanted, right, ratio of 2 integers. So this would be 495 over 99 plus 23 over 99, and we would end up with 518 over 99. Okay. Take a look at our next example. Find the sum of the telescoping series, summation of 1 over n times n plus 1. So one of the things we could do is we could separate that series into a partial fraction series, like a partial fraction decomposition. So it ends up becoming actually summation 1 to infinity of 1 over n minus 1 over n plus 1. And so from here, if we start figuring out the first few terms in the series, if we plug 1 in, we get 1 over 1 minus 1 over 1 plus 1 will be 2, plus, when n is 2, we would have 1 over 2 minus 1 over 2 plus 1 is 3, plus, when n is 3, we would have 1 over 3 minus 1 over 3 plus 1, 1 over 4. Right? So on and so forth. If we keep this going until, let's choose a variable, let's say k, we would have then 1 over k, and then minus 1 over k plus 1. Now I want to point out what happens. Well, notice we have the minus 1/2, and then from the next term, the plus 1/2. They will cancel. And then you get negative 1/3 plus 1/3. They will cancel. So on and so forth. The negative 1/4 will cancel. The 1 over k would cancel. So you're left with basically the first term minus and then the last term. Right, so we could say here s sub k, since we're using k, would be equal to 1 minus 1 over k plus 1. Now let's say we took the limit of this, right? Let's say we took the limit as k goes to infinity of 1 minus 1 over k plus 1. What happens? Well, when we have 1 over infinity plus 1, the plus 1 really doesn't matter here, but the 1 over infinity, that becomes 0. Right, so that goes to 0. So that means all we're left with here is 1. Okay, so we could say that the series would converge, the telescoping series would converge, and the sum would be 1. Okay, nth term test for a divergent series. So one reason that a series may fail to converge is that its terms don't become small. Okay, and here's a case where we have a series where the terms don't become small. So let's take a look at the series. If we start with 1, we would have 1 plus 1 over 1, so we would get 2 over 1. And then for n is 2, 2 plus 1 over 1, 2 plus 1 over 2, so that'll be 3 over 2. And then next one will be 3 plus 1 over 3, so that'll be 4 over 3. So on and so forth. And so we see that this is going to diverge. It's going to keep getting bigger and bigger and bigger. The first number is 2, and then 1.5, 1 1/3. And as you see, as we keep going in the series, whatever we have in the denominator, numerator will be 1 more than that. So that means as we keep going, the sum will just keep piling on and on and on. It'll keep adding by 1, a little bit more than that, every time we add another term. Okay, so the partial sum is going to eventually outgrow every previous partial sum. Okay, so therefore we would say that this one diverges. Alright, so let's take a look at Theorem 7 says if the series converges, then an approaches 0. And this implies that if we take the limit as n goes to infinity, the terms would have a limit of 0. The nth term test for divergence. The series diverges is if the limit as n approaches infinity of an fails to exist or is different from 0. Okay, so that's the nth term test for divergence. You take the limit as n approaches infinity of an, and that's the equation, that's the formula for the series, right, like we see up here. If it fails to exist, like it does not exist, or is different from 0, then we see that the series diverges. Okay. Okay, let's take a look at these examples. Okay, n squared. So here we take limit as n would go to infinity of n squared. Right, and so the limit here would be, if we take infinity and you have infinity squared, yeah, this would be an infinity. Right, so therefore this series would diverge. Okay, n plus 1 over n. So if we took the limit as n approaches infinity of n plus 1 over n, we could divide everything by n, and we get 1 plus 1 over n would be 0, right, which would be 1. And so the limit is not 0, right, so therefore this would diverge. Okay, here in this one, negative 1 to the n plus 1, so we do limit as n approaches infinity of negative 1 to the n plus 1. And here, for this limit, as we put numbers in for n, when n is 0, let's say when n is 1, since we're starting at 1. When n is 1, we get negative 1 squared, which is 1. When n is 2, we get negative 1 to the third, which is negative 1. And so this will alternate between negative 1 and positive 1, negative 1 and positive 1. So this is going to be oscillating. Okay, and we know from previous section that when it's oscillating, the limit does not exist. And therefore the series will diverge. Okay, and then here the summation. Let's do limit as n approaches infinity of negative n over 2n plus 5. We divide everything by n. So we have negative 1 over 2 plus, and this will be 0. So negative 1 over 2. And again, the limit for this is different from 0, right? So therefore, right, it's not equal to 0. So therefore this will diverge as well. Right. Okay, so that's the nth term test for divergence. Okay, let's take a look at example 8. Here in this one, we would have 1, and then for this group of 2, that becomes 1. For this group of 4, that becomes 1. For this group of 2 to the n, this will become 1. Right? So every cluster or every group will have infinitely many of these groups. So this will diverge as well. Right? This one will diverge because we have all these groups that will eventually sum to 1, and we keep adding 1 and 1, add another 1. So the sum will exceed the previous sums. And so therefore this will be a divergent series. Okay, we combine series, especially when we have two convergent series. Whenever we have two convergent series, we can add them term by term, subtract them term by term, multiply them by constants to make new convergent series. Okay. Every non-zero constant multiple of a divergent series diverges. And then we have if one series converges and another series diverges, and if we take the sum of the series or the difference of the series, in both cases they diverge. Okay. Let's take a look at the sum of the following series. So we can rewrite this as the sum of two series. We can say this is the sum of 3 to the n minus 1 over 6 to the n minus 1 minus 1 over 6 to the n minus 1. Okay, now the series on the left, we could say this is 3 over 6. They're both the same exponent, right? So we could say like this, 3/6 to the n minus 1, which will reduce to give us 1/2 to the n minus 1. This one over here, we could say this is 1 over 6 to the n minus 1. Okay, so we have two series like this. The r would be 1/2 in this one, r would be 1/6 in this one. Okay, if we plug 1 in, first term becomes 1 in both cases. Okay, so we have a equals 1, r equals 1/2, and then we have a equals 1 and r equals 1/6. Okay, so we're going to take the sum, find the sum of each series, and then we subtract them. Okay, so 1 over 1 minus 1/2. And then we're going to subtract 1 over 1 minus 1/6. So this one becomes 1 over 1/2, which is 2. And this one becomes 1 over 6, 6 minus 1, 6 is 5, 6. So 1 over 5, 6 would be 6 fifths. So 2 minus 6 fifths, that would be 10 fifths minus 6 fifths. So we would end up with 4 fifths. Okay, let's do another example. Let's find the sum of this series. We could rewrite this and say this is 4 times 1 over 2 to the n. So we say 4 times 1/2 to the n. Okay, we pull the 4 out. So we can say this is summation of 1/2 to the n. Okay, and so as n starts at 0 goes to infinity, first term in this series when we plug 0 in would be 1. R is 1/2. So we will do 4, and then we could do the summation here, 1 over 1 minus 1/2. And we know the summation there is 2. And we have 4 times 2, and we end up with 8. Okay. And then just a final note on how we could write series. We could always do what we call reindexing. We could start the index, the variable in the series, off at a different value if we wanted to. Now if we do that, we would adjust the formula slightly in the series so we end up with the same terms. Okay, so for example, another way we could write this is if we started at n equals 0 to infinity, and then this one would become 1 over 2 to the n. Okay, let's say we want to start off at a different value. Let's say n equals 5. Well, if that's the case, and we want the same terms in the series, then we would adjust the formula because we want that first term to be a 1. So we would say 2 to the, that would be 5 minus 5, so n minus 5. Okay, and now notice that'll give us the first term of 1, and then next will be n equals 6, so that would give us the 1/2, so on and so forth. Let's say we started off with a negative number. So then we had, let's say, n equals -4. So then this would then adjust, and we would have 2 to the n plus 4. -4 plus 4 would be 0. 2 to 0 would be 1. And then next would be -3. We plug -3 in, we get the 1/2, so on and so forth. Okay. So we could always do what we call reindexing. Change the index, but we adjust the formula so that the number of the terms stay exactly the same. Okay, any questions, just write me an email. I'll see you guys in class. Have a good day. We'll see you soon.